Hi everyone, I'm Alireza. I'm going to share with you a summary of a work that I did with Luigi Rizzo from Google during my PhD at KTH Royal Institute of Technology. And the aim of this project was to characterize the performance implications of IOMMU and IOTLB at multi-100 gigabit per second rates. As many of you know, emerging technologies and new applications such as AI, augmented reality, VM hosting, VR, 5G, and 6G demand a much higher bandwidth than traditional application, and this will put a greater demand on data centers. As a result of this, linkage speeds are getting faster and faster. For example, this figure shows the trend of linkage speeds in the last 40 years. And we can observe that we are getting closer to having a 1 terabit per second standard for Ethernet. However, introducing faster linkage speeds exposes networking elements to packets at a higher rate. For instance, if we consider a 100 gigabit per second link, theoretically, a server receiving minimal sized frames receives a new frame every 6.72 nanosecond, which is around 10 times faster than the memory access latency. Therefore, multi-100 gigabit per second networks cannot tolerate memory accesses, as it could increase service time and cause a tremendous amount of buffering and packet loss. Additionally, the communication between different system components could also become a bottleneck at high rates. Next, we will go a bit deeper to understand what are the communication bottlenecks when transferring packets between a NIC and CPU while receiving packets at multi-100 gigabit per second rates. In the data path between the NIC and CPU, typically NIC DMAs packets to CPU's memory, and this is done by accessing the host memory via PCIe bus. In some architectures, NIC can also access last-level cache of the processor, which will reduce the DMA latency. For example, Intel's Xeon processors has a feature called DDIO, or Data Direct I/O technology, which makes it possible to DMA directly to and from last-level cache and avoid expensive memory accesses. And finally, after DMAing the data to the host memory, CPU cores responsible for processing the data have to load them into their cache memories to be able to process them. To access host memory and DMA data, NIC requires memory addresses of buffers. Without IOMMU, CPU provides the physical addresses of the buffers to the NIC. But when we enable IOMMU, the CPU provides an IO virtual address instead of physical address to the NIC. By doing so, IOMMU restricts the DMAs to only a specific memory regions, and this will provide IO security and facilitates virtualization and backward compatibility. However, the IO controller needs to translate these virtual addresses or IOVAs to physical addresses for every IO request during the DMA process, and this is done based on some predefined translation entries which are registered beforehand, and this could cause some performance overhead. To minimize this overhead, similar to IOMMU counterpart, MMU or Memory Management Unit, processors usually use a cache called IOTLB to accelerate these translations. All the components involved in the data path must sustain line rate. If there is short-term variability, this can be absorbed typically by un-NIC buffers, but eventually each component could cause a bandwidth bottleneck in the system. For instance, PCIe 4 supports 16 gigabit per second per lane, which will be translated to 256 gigabit per second bandwidth cap for a 16-lane PCIe bus. Newer PCIe versions try to address this bandwidth bottleneck. For example, PCIe 5 doubles this rate. Similarly, other components such as memory interconnect, DDIO, memory, IOMMU, or IOTLB could also become bottlenecks. In addition to bandwidth, since each component supports limited amount of buffering, a high bandwidth delay product could also cause a bottleneck. If we assume that each transaction keeps a buffer busy for some time t, the throughput would be less than buffer size divided by this time t. For example, PCIe can typically buffer around 32 to 64 KB per direction, and in case of PCI memory read, the read buffer, also known as completion buffer, stays busy for the time between a request is sent and the data is received. And this may cause a bandwidth delay product bottleneck. For example, 64 KB of completion buffers allows only for 2.6 microsecond read latency. For PCIe memory writes, the write buffer or credits stays busy for the time a request is sent until the memory accepts the request. And in this case, 32 KB of credits allows only for 1.3 microsecond write latency. Now that we have a better understanding of communication bottlenecks in the system, we are going to only focus on IOMMU and IOTLB in the rest of this talk. IO subsystem has an upper bound for the number of outstanding DMA transactions, and this will implicitly create a throughput bottleneck. This bottleneck is proportional to the buffer size that we just explained in the previous slide, and also is inversely proportional to the time which it takes to complete an IO transaction. And this time can be both dependent on the memory-related transaction and also the translation time done by the IOMMU or IOTLB. Ideally, this bottleneck has a much higher value than the data path rate. However, in cases where IO transaction time increases, the value of this bottleneck decreases and it may cause a throughput drop. The IOMMU overhead are mainly due to three main reasons. First, IOVA allocation and deallocation during allocating and deallocating the pages cause some overhead. Secondly, a higher degree of security requires invalidating and flushing IOTLB every time we remove a mapping. And finally, going beyond the capacity of IOTLB causes misses, which will increase the T of IOMMU in the equation that we saw earlier, and it will reduce the performance. The first two overheads typically show up as additional CPU load, and they have been studied and optimized by prior works. For example, the Linux kernel already implements deferred IOTLB invalidations to amortize the cost of flushing over multiple unmappings. In this talk, we focused on the last overhead, which is IOTLB misses, and it does not show up as additional CPU load. IOTLB misses are affected mainly by the size and management policy of IOTLB and also the memory request patterns. The former is hardware dependent and may vary for different vendors as they implement IOTLB differently. The latter can be affected by various system configurations such as MTU size, packet drop, packet rate, and also offloading features such as LRO or TCO, and also the Linux and the device driver buffer management scheme could also affect the number of IOTLB misses. IOTLB usually supports different page size mappings, such as for KB, 2 MB, and 1 GB page mappings. However, the Linux kernel is currently using only 4 KB mappings, which imposes a lot of performance overhead, as we would require more translation entries. In this talk, we focus on the second factor and try to characterize the impact of various parameters on the number of IOTLB misses. To do so, we set up a testbed with 2 servers using Intel Xeon Ice Lake processors, which are equipped with 200 gigabit per second NVIDIA ConnectX NICs. We use one server as iPerf client and the other one as iPerf server. We run throughput test with 32 threads, 384 TCP connections on Linux kernel 5.15. And initially, we only focus on 1500 MTU sizes. This figure shows the throughput of an iPerf server versus the generated rate by the iPerf client. We can see that without IOMMU, the throughput increases almost linearly and reaches the maximum achievable rate. But enabling IOMMU on the receiver side causes a significant throughput drop, up to around 20%. However, if we now look at the CPU utilization of the receiver for the same experiment in the bottom figure, we can see that IOMMU overhead is not due to the unavailability of CPU resources. We have almost around 40% unused CPU resources at the point where throughput becomes saturated. To better understand the root cause of the throughput drop, we also measured the IOTLB misses in this experiment. And we report it as the number of misses per megabyte, which represent the number of misses per unit of data. And this metric makes it possible to compare the misses across different rates and different configurations. This figure shows the average number of IOTLB misses per megabyte and also the throughput drop due to IOMMU versus the generated rate, which is basically the result for the same experiment that we saw earlier. We can easily notice a sudden jump at the number of IOTLB misses per megabyte around 130 gigabit per second. That is the same rate as the saturated throughput saturation point in the previous figure. And this result shows that IOTLB misses will cause a significant throughput drop after a certain number. In other words, excessive IOTLB misses builds up a wall and can cause throughput drop. Next, we try to do some back-of-the-envelope calculations to better understand why we see this jump in the number of IOTLB misses. In case of this experiment where we use 1500 MTU sizes, each RX buffer is 2 KB and only uses half a 4 KB page. For each megabyte, optimally, we require around 725 RX buffers, which will be translated into 362 4 KB pages, only if the device driver does not allocate more pages. Initially, all the RX descriptors are contiguous, which means that only accessing the first buffer of a page will cause an IOTLB miss, and the next part of the page or the second translation can be served from the IOTLB and it will be a hit. However, later, due to packet drops and a slow buffer recycling, the buffers get shuffled and affects the order of descriptors. Consequently, both buffers belonging to the same 4 KB page will not be back-to-back and may experience IOTLB miss, which is at least one additional IOTLB miss compared to the initial system condition. So now if we go back to the results, we will see that initially the receiver experiences around 442 IOTLB misses per megabyte, which is roughly in the same order as our calculations. Note that the extra 80 misses may be due to using multiple queues and also a slow buffer recycling. Later, after 130 gigabit per second, the number of misses increases, and we think that this increase is correlated with buffer shuffling. To test our hypothesis, we did a similar calculation and also experiments for larger MTU sizes, where we use 4 KB buffers instead of 2 KB buffers. In this case, a megabyte requires around 288 4 KB pages or RX buffers as they use the full page, which is much fewer than the previous case with 1500 MTU sizes. And if we look at the actual measurements, we see that the number of IOTLB has also decreased. And this has pushed the IOTLB wall to a much higher rate. In this experiment, the throughput drop happens at 150 gigabit per second instead of 130 gigabit per second. And this suggests that a modest decrease in the number of IOTLB misses per megabyte can shift the rate at which throughput becomes a bottleneck. Next, we looked at the impact of TSO on the number of IOTLB misses. TSO offloads TCP segmentation to the NIC, and this will result in fewer IOMMU translation as the messages can be transferred to NIC in larger chunks. If we look at the number of IOTLB misses when TSO is enabled and disabled, we notice that TSO can significantly reduce the number of IOTLB misses per megabyte, especially for smaller MTU sizes. And this decrease in the number of IOTLB misses results in less throughput drop and can help us overcome the IOTLB wall. We also analyzed the impact of buffer shuffling due to packet drops and TCP retransmissions, and noticed that this will also increase the number of IOTLB misses. To do so, we developed a kernel patch that artificially drops packets in the Linux kernel stack to induce TCP retransmissions. This figure is showing the average number of IOTLB misses per megabyte for different MTU sizes and different packet drop rates. And we observed that the higher the drop rate, the higher the number of IOTLB misses per megabyte, which can be basically translated to more overheads when there is higher drop rates. An obvious way to mitigate IOTLB wall is to use larger IOTLB mappings to reduce the number of entries and misses. To do so, we modified PagePool API in the Linux kernel to allocate 2 MB huge pages and split them into 512 4 KB pages at runtime instead of allocating 4 KB pages in bulk. This figure shows the throughput of an iPerf server, similar to the previous experiment that we saw for different IOMMU configuration. And we clearly see that using 2 MB IOTLB mappings can recover the throughput drop introduced by IOMMU. This observation may not be new, as we already know the benefits of huge pages from kernel bypass frameworks such as DPDK. However, despite many previous efforts, the Linux kernel is not using huge pages due to many challenges. Next, I will go over some relevant challenges in the context of IOMMU. The first challenge is related to page allocation and its costs. Allocating 2 megabyte pages directly translating to allocating 512 contiguous 4 KB pages, which is much more difficult. And this potentially requires more expensive compaction process, as all these pages need to be coalesced together to recycle into a new 2 megabyte page. And if this is not performed in time, it could cause a tremendous amount of memory fragmentation in long-running systems. To prevent allocation cost, it's possible to reserve a few gigabyte or megabyte of memory at boot time based on the expected bandwidth delay product. But this may cause memory stranding if the memory is not utilized properly by the system. Moreover, we also noticed that existing NIC drivers continually allocate pages due to a slow recycling, so it also may be difficult to operate with a fixed size pre-allocated page pool. Finally, when we use larger mappings, the effect of locality and buffer management becomes more significant, as it will be much more difficult to ensure locality for 512 contiguous pages instead of 2, which were used for 4 KB pages. Consequently, the system might experience more severe buffer shuffling. To better understand this, we perform an experiment where we measure the number of IOTLB misses over time in 3 different scenarios. The first scenario considers the case where we allow continual page allocation, and this is done by our patch to the PagePool API, where we allocate 2 megabyte pages and split them into 512 4 kilobyte pages. And the second and third scenarios, we again slightly modify the PagePool API to use a fixed size pre-allocated pool with 256 and 512 2 megabyte huge pages. This figure shows the number of IOTLB misses over time for these 3 scenarios, and we can observe that IOTLB misses increase significantly over time when we use fixed size pools as a result of buffer shuffling. Furthermore, we also noticed that the fixed size pool can be depleted due to a slow buffer recycling only after a few minutes. To conclude, today I briefly discussed the new bottlenecks that could arise when shifting toward high link speeds. Then we modeled these bottlenecks and characterized the performance of IOTLB at 200 gigabit per second in different configurations. And finally, we discussed the challenges of using larger IOTLB mappings in the Linux kernel, which may be necessary to overcome upcoming 200 and 400 gigabit per second networking. If you're interested to learn more, we have a journal publication on this topic where you can find by scanning this QR code. And also our source code, both for the kernel patches and the benchmarks, are publicly available on GitHub. With this, I conclude my talk. Thanks for listening, and I'm happy to take questions.
Hi, thanks. Great talk. Wonderful to see numbers like this. A question for you on your first experiment where you doubled the size of the message and you only saw like a 10 or 20% increase in the throughput at which you ran into problems. That doesn't make sense to me. I would assume if you double the size of your messages, you should be able to send twice as much bandwidth before you start running into problems. Can you help me understand why didn't you see a much greater improvement in the throughput when you increase the message size?
Well, so I think the IOTLB is still a cap, right? So I didn't do the calculation why it's not 2x, but if you look at the calculation for the number of misses, it's not like it doesn't surpass, so it doesn't get reduced as much as so go below the capacity of the IOTLB, so that it doesn't cause a bottleneck. So maybe that's the reason. But I don't have like a proper answer for you why it's not doubled.
And do you agree intuitively it would make sense that it should double, or is there something I'm missing with my intuition?
So I think there are multiple factors affecting here. So I mean, intuitively, yes, but I cannot agree on it before measuring more to see what could be the other bottlenecks that we miss in our experiments. Does that make sense?
Yeah, thanks.
Thank you.
Do you have any data on this on other platforms like ARM64 or something? Do you know how this correlates against changes, different hardware and stuff like that?
We did measurements on AMD and AMD EPYC Milan 3rd generation and Intel Xeon Ice Lake processors. So in the AMD case, I didn't show the results, but you can refer to the paper and see. But in the case of AMD, the IOTLB is implemented slightly differently. Based on my understanding, there are two levels. It's hierarchical, so the amount of misses has less impact on throughput. But we observed that in case of AMD, enabling IOMMU doesn't affect throughput as much. But for a specific processor that we tested, we had an issue achieving line rate for MTU sizes less than 3,000 bytes. So it was a bit different from Intel. That's why I didn't show in the slides. But all the results and benchmarks are available online. So if you think this would make sense to check on other architectures, I think it's possible to tweak it a bit and run on ARM, for example.
Yeah, I can add that we were running NXP ARM64 systems, and we had to turn off the IOMMU because we couldn't even hit 20 gigabits in traffic with, I think, 500 bytes packets or something. It wasn't our main point of looking into at that point, so we didn't investigate further. But it seems to be a real problem there as well.
Yeah, if I could add, a couple of things. Each platform is different in this respect. The core of the problem is that we are hitting a bandwidth delay bottleneck, and so as long as we are below this bandwidth delay bottleneck, which is the amount of buffering we have, everything is fine. Every little thing that moves us beyond that causes performance drops or packet drops, depending on the direction you're operating. So I think the message is be aware of this problem, run measurement, and if you find an issue, try to tweak the configuration of the platform, increase page sizes, etc., to understand whether this is the problem we are facing or something else. And if this is the problem we are facing, there are ways to attack it, like improving memory locality, trying to reduce the number of IOTLB misses, and using larger pages, and so on.
Yeah, you can go first, yeah.
Another question for you. If I understand the way buffer allocation works in Linux, every buffer has at least two different memory extents. There's at least a relatively small one in the SKB itself, the linear part, which has typically headers, and then there'll be the data, which is allocated separately. So it seems like that means that the NIC has to do two different IOMMU lookups, minimum for each packet. So would it make sense to actually try and change the way SKBs are allocated so that, in fact, they're just a single chunk, effectively get rid of the linear part and allocate the entire SKB out of the frags in order to cut by a factor of 2 the number of translations that the IOMMU would have to handle?
That might help to some extent. I have to say that depending on the driver, the buffers that are, especially on the receive side, the buffers that are allocated for the headers are all contiguous and in one chunk. So that part is mostly free in terms of IOMMU translation. On the transmit side is different. And what you suggested makes sense.
So my new favorite topic, hardware GRO. Did you get a chance to? What do you think the effect would be as opposed to software GRO on the TLB?
So we didn't check the impact of GRO, but we looked into the impact of LRO. And I mean, any sort of offloading that would affect the number of transactions, PCI transactions, and the number of translations could potentially reduce the number of misses. But as we saw in the experiment, the reductions should be to an extent that could help the throughput. So if it's not enough, so we still struggle. And in our case, when we were looking into the impact of LRO, the number of misses were getting lower, but the throughput was not changing. So it was not helping as much. And I assume it would be the same for GRO, right?
Yeah, I guess the CPU though, you saw it go down, or the utilization went down.
Yeah, but in our case, so first we try to ensure that we are running experiments in a case that we are not in the CPU bound region. So we optimize all the parameters to have enough CPU capacity. So we are only taking into account the IO bottleneck or IOTLB. So in both cases, we could achieve line rate with or without LRO. So that was not an issue, but it could affect the CPU utilization for sure.
Okay, thanks. It's okay, good. One more question and then we'll wrap it up.
So just one thought. In the past, I've seen this kind of thing before with PowerPC. And one approach I took was to look at a copy break solution for smaller buffer sizes. So for example, in the TSO case, you have one buffer that you just keep around, and you see a header come by that's okay, that's really small, it's going to be expensive. Copy it in and just keep that static mapping around for basically catching those. Have you thought about investigating something like that as a solution for some of the higher bandwidth cases?
Your suggestion, I think, makes sense, but we haven't explored it. But basically, it somehow increase locality of the entries in IOTLB. So if we keep using the same entry for different packets, so it's the probability of staying in the cache is higher. So we probably get a beat rather than a miss, right?
Right. Yeah. It essentially be an aggregation. You create one mapping and then you copy several buffers into it, so you only are having to access that one buffer.
Yeah.
Sorry, I missed one piece actually. Page pool wasn't around when you're doing this. And were you using page? It sounded like you're using page pool of a huge page.
We were using page pool, but this is like kernel 5.15.
All right. Thank you.
Thank you.